Hello everybody, this is a mid-semester group project review and our topic is mathematical modeling of recovery of crude oil using solvent. What is crude oil? Crude oil is a mixture of different hydrocarbons, all of varying lengths and complexities, different number of carbon atoms in different hydrocarbons. How they are formed? Large quantities of dead organisms are buried under the earth crust, and due to high heat and high pressure they are converted into the petroleum product. The hydrocarbons in crude oil are mostly alkanes, cycloalkanes and aromatic hydrocarbons. Crude oil may also be found in a semi-solid form mixed with sand and water, and it is essentially referred to as crude bitumen. I have mentioned some elemental composition of crude oil, that is carbon is varying from 83 to 85%, hydrogen is 10 to 14%, nitrogen is 0.1 to 2%, and so on. They are categorized in two categories, was a light crude oil, heavy crude oil. Light crude oil are having low viscosity, low specific gravity and high API gravity. API gravity is American Petroleum Institute gravity. I have given the formula in the below. According to NYMEX, New York Mercantile Exchange, I have given some range of API gravity values which characterize light crude oil, or whether it is a light crude oil or heavy crude oil, which differentiates. Heavy crude oil is closely related to natural bitumen from oil sands, and since natural bitumen is having a very high viscosity around 10,000 centipoise, heavy crude oil is having high specific gravity, low API gravity value, and they are resemble to the residue of refining from the refining of light oil. After refining of light oil, the residue remains as of highly viscous, and that is similar to the heavy crude oil. Since it is very highly viscous, so it is not possible to flow by the natural pressure difference, so we use some special extraction techniques such as steam assisted gravity drainage, steam injection, vapor extraction, etc. Our study will be focused on heavy crude oil. Crude oil reservoirs. Three conditions are must for an oil reservoir to form. A source rock rich in hydrocarbon material must be there and buried deeply enough for subterranean heat to cook it into oil. A porous and permeable reservoir rock must be there which is able to trap that cooked oil and where it can accumulate. A cap rock must be there to prevent the oil from escaping from the surface. As in the figure I have mentioned, I have shown like green part is source, above that reservoir, above that violet part is seal, and above the seal we called it overburden, and below the source we called it underburden. Different techniques of recovery I have mentioned here. I have mentioned three techniques. First is SAGD, steam assisted gravity drainage, in which what we did is we injected steam through a well into the reservoir, and as the steam comes in contact with the heavy oil, it condensed at the surface and supplying its latent heat to the deposit, which lowers down its viscosity, and the heat transfer mechanism occurs there. Less viscous layer thus forms drain down due to gravity force along the interface through that porous matrix. As first layer is removed, new layer is exposed to the steam, and this process continues until we reached an uneconomical level. Another process is VAPEX, vapor extraction. A vaporized solvent is used instead of using steam, and this injected solvent dissolve into the heavy oil through molecular diffusion and convective dispersion, and the solvent dissolutions mechanism occur in this process. And we use solvent like light alkanes, for example propane, and our study of this model will be based on this specific process. Advantages over SAGD: it doesn't require steam injection, so no capital investment for hot steam generation and wastewater treatment. More environmental friendly because no fuel burning is happening. In SAGD, heat losses to overburden and underburden become important as recovery process matures, so this process, SAGD process, may be sometimes less energy efficient for economical production. And I've mentioned the third process is solvent aided SAGD, which is a hybrid process in which we co-inject vaporized solvent along with the steam In this process, both the heat transfer and solvent dissolution process take place simultaneously to lower down the viscosity of that rock matrix. Advantages of this is like at a given injection pressure, lower operating temperature is required, so lower energy required and less flue gas emission. Since we are steam is being supported by the solvent dissolution process, so less steam is required, and as a result steam oil ratio is less fuel required in steam generation, and thus less carbon dioxide production take place. In comparison to solvent only process, solvent is more effective in mobilizing bitumen in this process, and due to higher temperature its diffusivity is higher and high degree of physical dispersion in this process. Our problem statement is we are going to model mathematically the recovery of crude oil using solvent, and we will be focusing on VAPEX process. Our model involves characterization of transition zone, evolution of solvent chamber, and calculating oil production rate. Here I have mentioned some literature review, like I have the pre-proposed already, these models have already been proposed by different scientists, and the very basic model is BM model. The earliest model is BM model, that is Butler-Mokres model, and these are some few models. Here are some more models from the literature. This is the schematic diagram of our model, which we are going to on which we are going to model our process, or model our study. Model description includes since upward growth of solvent chamber is very unstable and very minor contribution towards the total oil production, so we are going to neglect it, and we will be focusing on only the lateral expansion of chamber after it has reached at the top means after it has reached at the cap rock. At early stage a linear interface is considered, but on the later stage we will consider as a parabolic interface, and we will be comparing the results with the linear interface. Mixing of heavy oil and solvent and drainage of solvent diluted oil take place at solvent chamber boundary, and we called it as a transition zone. Across transition zone, solvent concentration decreases gradually from maximum value, that is saturation concentration, to nearly zero, where we define as concentration boundary layer. Major recovery mechanism occurring in the transition zone are mass transfer, including molecular diffusion and convective dispersion, multiphase flow, gravity drainage, and surface renewal. Here are the assumptions. We are assuming homogeneous and isotropic porosity and permeability distribution. It means porosity and permeability will be uniform throughout our matrix. Solvent injection at constant pressure and temperature. Bitumen, due to high viscosity, we consider as bitumen is immobile in the deep into the deep part of the reservoir. Interface temperature is same as solvent temperature, and solvent concentration at interface is equilibrium solubility of solvent at operating pressure and temperature. We are considering direction of mass transfer perpendicular to the interface, and gravity drainage direction along the interface. Solvent diluted oil by means of gravity force only, we will be neglecting other forces. Here, as we consider the first mechanism is the mass transfer mechanism. At the transition zone, oil solvent mixing process can be characterized, can be modeled using fixed second law, that is del C by del T is equal to del square C by del X square, where C is equal to solvent concentration in solvent diluted oil, and D is effective diffusivity, which incorporates all mixing mechanisms. To simplify the model, I have assumed only one effective diffusivity, and which includes both the molecular diffusion and convective dispersion. The basic assumption I have assumed is due to small solubility of vaporized solvent in heavy oil, I have assumed D as a constant. I have given some boundary conditions to solve the equation first. The basic problem with the equation first is the variable involved is X, which is time dependent variable, and the problem is a moving boundary problem. So to solve the equation 1, it is required to convert it as a fixed boundary problem. So we are going to define a new parameter, that is eta, and which is x minus integration 0 to 2 0 to t ut dt. U is velocity of moving boundary normal to the solvent chamber boundary. Substituting fifth equation into 1 to 4 equations and using chain rule, we come through equation number 6 and revise boundary conditions. So we have to solve this equation 6 with the help of these revised boundary conditions to get the profile. Another process is gravity drainage. Since the matrix is porous, so we will be using Darcy law to calculate drainage velocity, and thus we will be able to calculate the oil production rate. So here I have equation 10 is Darcy law for multi-phase flow. I have assumed multi-phase flow where capital K is absolute permeability, KRO is oil phase relative permeability, and other parameters. So we have to solve this equation number 6 and equation number 10 to further proceed upward mode. Thank you. For the progress in this model will be done till end semester.